Hello everyone. So today's topic of discussion is current series feedback connections. The topic is in continuation to other feedback connection schemes. We have done voltage series and voltage shunt so far. In voltage series feedback connection, the feedback network is usually connected in parallel to the output section of the network, whereas connected in series at the input terminal of the network. On the other side, for voltage shunt connection, the output section is connected in similar way to the feedback network as we were doing for voltage series networks. Means feedback is usually connected in parallel to the forward path at output terminal. But the things slightly changes at input section if we compare it with the voltage series part. In voltage shunt, the feedback network is usually connected in parallel to the input section input terminals. Now for current feedback type networks, we'll connect the feedback in series with the output terminals, and that remains valid for current series as well as for current shunt networks. And we can see a series connection at the input side as well, whereas for current shunt it will slightly change. Means we'll see a parallel connection for current shunt networks that we'll discuss later on. For this network here, we are supplying a input voltage value that is Vs, and we are getting I naught as the output. Now suppose the gain of the amplifier that we can see in this brown box is A. Then this Vi is the voltage or potential developed across the input terminals of the transistor. So Vi is basically the input for this one. So Vi multiply gain will be the output current I naught. And actually in this case, we are basically tapping this output current I naught through this feedback network with a gain beta, so that my potential, that feedback potential will become equal to beta multiply I naught, and then is fed to the mixer for further processing. So here also we'll be calculating the gain, obviously, then ZIF, the feedback input impedance, and feedback output impedance, right? That will see at this terminal is the input feedback impedance, and from this side it is the output feedback impedance. Now let us continue with the mathematical part. First, say we have to calculate the gain. So I'll represent this gain as A of F, that is feedback gain, and obviously this will be output value over input value. So input here is Vs, obviously we have to divide it by Vs, and what is the output thing here? I naught, right? So I naught by Vs, that is the feedback gain. Now we know the values at mixer. Vi is equal to Vs minus Vf, right? At this point here. Okay, so we can easily get this Vs value from here. Vs will be Vi plus Vf, correct? And Vf, if we see, is the beta times I naught. So let's replace this value from here. Let's write beta times I naught, and we know that I naught is the output we are getting after passing through this amplifier with gain A. So we can replace this I naught as well, right? So this Vs equation will become equal to Vi plus beta times, in place of I naught I can write A into Vi. Now let us substitute this value of Vs in AF equation, so that my AF equation will become equal to I naught over, I'll replace this Vs with this whole thing, Vi plus beta A Vi, or I can rewrite this thing, and obviously I'll replace this numerator value with the same amount, A times Vi, over in the denominator I'll take Vi common. So remaining thing in the bracket is 1 plus beta times A. Now Vi can easily get cancelled out, right, in the numerator and denominator, so that my AF equation can be further reduced to A over 1 plus beta times A. So this is the final feedback gain value. So from here we can conclude that without feedback the gain could have been A only, right? But this time, as the negative feedback is introduced, this gain A is being reduced by this factor, right, 1 plus beta A, and that thing actually remains common for all the feedback connection types. Now let's move on to calculations of input impedance, the effect on input impedance of feedback. Now let us first assume the input feedback impedance value to be ZIF, and ZOF will be the output feedback impedance. Now mathematically we can write this ZIF to be equal to the input potential, that is Vs. You can see Vs, and the input current is II, right? Now Vs can be further written as we know the value from calculations done in previous section, that is Vi. I'm writing it directly, A beta Vi over II, right? Now let us take a few things common. Let us take the Vi common from here. So ZIF will become equal to Vi 1 plus beta times A over II. Now we know Vi is the input potential for transistor device, and the current is the input current II, and the ratio of this Vi to the II is nothing but Zi. So we can replace this thing with Zi, right? So ZIF will become equal to Zi multiply 1 plus beta times A, right? So that is nothing but the input feedback impedance value. So from here we can conclude that the input impedance value actually is increased by a factor 1 plus beta A. Without feedback, without negative feedback, the impedance could have been Zi only, right? We can see Zi, right? But with the introduction of feedback, the input impedance Zi is basically scaled by a value 1 plus beta A. So we have already assumed the output feedback impedance to be ZOF, right? So to calculate ZOF, we'll be making few assumptions on the basis of Thevenin's networks. Basically, we are trying to calculate the Thevenin's resistance ZOF. Okay. So very first assumption is that make all the independent sources equal to 0. Independent source here is Vs, that will make 0 by simply putting a short circuit across these two terminals, right? And the independent sources, they'll remain in the network as it is. This I0 is the independent source, dependent source. It is actually depending on Vi value. In addition, we'll put a open circuit across RL. Instead, we'll place one voltage source with potential V0 across this RL. And let's say this V0 is actually contributing a current I0 through this network, so that the ZOF can be written mathematically as V0 over I0, the current contributed by V0. Now let us calculate the value of I0 from here. I0 will become, if we apply KCL at this node, I'll name it node A. So there are two currents actually, one is flowing towards this side and one is flowing towards this side. So I0 will be actually the sum of two currents, and thereafter they are getting added up again at suppose at node B. So I0 will be sum of this current through Z0. It will be V0 over Z0, right? Plus AVI, and we know Vi is the output of the mixer, which can be written as Vs minus Vf, but Vs is already made 0, so it will become minus of Vf, and Vf we know is the output of feedback amplifier, that is beta times I0. So I'll write it minus of beta times I0 in place of Vi, right? So let us replace the Vi term in I0, that is V0 by Z0 plus A. In place of this plus sign, I'll replace it with negative sign, minus of A beta I0. Now let us take all the I0 values on one side and take I0 common from them. 1 plus A multiply beta equals V0 over Z0. If we rearrange the equation a bit, it will become V0 over I0, and Z0 will simply get multiplied with 1 plus beta times A, right? So that is nothing but Z of output feedback impedance, we can say ZOF, and this again implies that we can conclude from here that the output impedance basically is increased by an amount 1 plus beta A. Therefore, in current series type connection, the input impedance as well as the output impedance, they are both increased by same amount, that is 1 plus beta A. So that is all for now. We'll continue with one more technique in next class. Thank you and have a nice day.